We are Team IOTAA from the University of Alberta under the mentorship of Dr. Ashwin Iyer and with assistance from graduate student Nabil Khalid.
My name is Alex Marie.
I'm Rochelle Lee.
I'm David Halowski.
And I'm Josue Salaya.
The goal of our project was to create a local positioning system that utilized RFID reader and tag technology and miniaturized antennas to track the movement of objects in real time.
I worked on the antennas of the project.
I worked with the visualization system.
I developed energy harvester systems.
And I work on the embedded system.
We are proud to present and show you the work that we have accomplished so far.
The system was not able to determine the distance between a reader and a tag, hence triangulation was not possible. Two hypotheses were formulated to try to explain the problem, which were the presence of electronic devices operating in the 915 MHz ISM band, and multipath interference corrupting the phase information received by the reader. A test was conducted in an anechoic chamber to rule out or confirm any of the hypotheses. After the test was carried out, the result was the same observed outside the chamber. The system is not able to measure the absolute distance, nor do the phase measurement reflect the monotonically increasing distance of the tag. It was found out that the selected reader imposed some limitations, where the in-phase I and quadrature Q received signal strength indicator or RSSI values are always positive. Thus, the calculated phase is always between 0 and 90 degrees. The reader provides a phase bit that indicates the sign of the Q over I ratio, though this is not sufficient to determine the phase quadrant. While absolute distance was not measured by the system, changes in distance are reflected in the phase-based measurements. This detection scheme was leveraged to create an interface capable of detecting when tags are in motion and when they are stationary.
The visualization system showcases the status of each tag with respect to each reader. If the measured distance changes enough from one measurement to the next, that tag is classified as moving. If the tag to reader distance stays relatively constant, the tag is classified as stationary. If the reader does not detect the tag, it is classified as out of range. These classifications are updated in real time and the visualization system is updated accordingly.
Hello! So I'm covered with voltmeters because I am showcasing our two energy harvesters. The RFID chips that we chose can either be operated in passive mode, in which case they're being powered only by incident RF signal, or they can be powered actively. And the benefit of that is when we hook them up to a battery, we reduce intermittency problems, because of course they have a constant power source, and secondly, we can increase their range because their sensitivity is increased. Now, the first and simplest of these two harvesters is the solar harvester here. And what I have is just on an armband, a really interesting 3D printed housing, and it is showing two 1.2 watt solar panels that are high efficiency, about 22% efficient. It is coupled with, which can't be seen, but a lithium battery in here, and then it uses what is called an MPPT charger, which is just a special maximum power point tracking solar charger. It's used because solar panels have pretty terrible load regulation, and this uses an algorithm to help maintain the voltage where the solar panels output the most power. So as we can see here, on even a pretty gloomy day, you're probably getting 6, 7, even 8 volts, which is more than enough on a sunny day to make sure that we can charge as long as the person is facing anything, even incident light in a building, as long as it's bright enough. And the more complex of the two units is the electromechanical harvester. And it is shown here on my knee in a very interesting way. Now we have a bipolar DC stepper motor here, which produces a DC square wave. I should say an AC square wave of DC values. Here it's rectified in 2 stages because it is bipolar. And then we go to another lithium charger, and of course we have a lithium battery here. This is a lithium iron phosphate battery, type of lithium chemistry, 3.3 volts nominal. More importantly, it's a little bit safer to wear because it does not have thermal runaway concerns compared to most lithium chemistries. Now the interesting thing here is we again use a solar panel, a solar charger here, because it turns out the maximum power point tracking algorithm really helps to regulate the negotiation between how much of a load is felt here, I should say output impedance, and how much is felt by the generator here. And it turns out we can actually have a significant increase in power output, or I should say power efficiency of this generator system. So lastly, I'll just show you on this knee brace, we have a carbon fiber nylon 3D printed gearbox with about a 16:1 gear ratio. And as you can see, when I bend my knee, I end up moving this stepper motor and we end up generating power. And we can take a look here that as I'm just pumping my leg here, I'm making a small amount of current. There's some room for improvement with a greater gear ratio, but for now it still demonstrates that we can make some amount of power here. The benefit, of course, is that then we have essentially perpetual active power in the RFID tags, either through solar when the person is not moving, or when they are on the go through this electromechanical harvester.
The inherently matched lambda-byte folded dipole design did not exhibit a practical read range, and was therefore not used for the demonstration of movement detection. As is seen on screen, this dipole achieved an approximate 15 cm read range, much lower than those reported in the original publications on which this design was based. The suspected reason for this disparity in performance is poor conjugate matching. While good matching was achieved in full-wave simulation, manufacturing tolerances are large enough such that it is possible for the matching bandwidth to be shifted outside the 915 MHz ISM band. This highlights a disadvantage of narrowband antennas and associated practical challenge with antenna miniaturization. Such antennas may be more sensitive to variation in fabrication than non-miniaturized counterparts. Fortunately, this project is still able to be demonstrated with miniaturized CP antennas.
Thank you for viewing the demonstration of our project. We would like to extend our thank you to the IEEE Antennas and Propagation Society for the support of this project, the mentorship of Professor Iyer, and of Nabil.